So in this video, let's graph the last trigonometric function, which is y is equal to tangent of x. And when we're graphing the y is tangent of x, using the properties and knowledge we applied for graphing the y sine x, cosine x, we'll be able to graphing on the current plane. So let's start off by thinking the angle rotations and new definition of trigonometric functions on the unit circle, which is a circle with the radius or half of the diameter of 1 that is already set up right here. So I'll go a little bit faster than before because this is a review of what we've done so far on the unit circle. So there is an angle rotation 0, which is another way to say 2 pi radian, with a coordinate of 1, 0 using the properties where the unit circle is a circle with a radius of 1. And as it rotates to 90 degrees and reaches the pi over 2 radians, then the coordinate will be 0, positive 1, where x is 0 and y is positive 1. And as it rotates to pi radian, which is 180 degrees, then the coordinate will be negative 1, 0. And as it gets to 3 pi over 2 radian, which is 270 degrees in terms of the degree mode, then the coordinate will be 0, negative 1. And lastly, as the angle finish is period or the cycle on the unit circle, then the coordinate will get back to 1, 0. And this was the basic setup for a unit circle. And now let's think about the random point or random the angular rotations on the unit circle to define the new definition of trigonometric functions. I rearranged this unit circle, and now let's think about the random angle rotations on the unit circle. Let's see if that is the data. And just like we talked about in the previous videos, then we'll be able to think about its coordinate right here. So we can naturally come to realize, because we talked about in a lot of videos, that the coordinate will be the cosine theta, sine theta, because of the property of unit circle. And if you're not familiar with it, you need to go back to my previous videos and think about it more. That means the cosine theta is the x coordinate, and the sine theta will be the y coordinate, in this case, according to the angle rotations theta. So this was the angle rotations theta, and there are totally 3 main angle rotations or central angle that we call it as the special angle. And those special angles are pi over 6 radian, pi over 4 radian, as well as the pi over 3 radian, which are 60 degrees, 45 degrees, as well as 30 degrees. So pi over 6 is 30 degrees, 45 degrees, and 60 degrees. And they have their own coordinate on the unit circle as we rotate them on the unit circle. So let's review quickly first with the pi over 6 radian. So let's assume that this green line is rotated pi over 6 radian for a total. And obviously the pi over 6 radian is going to be 30 degrees. And as it rotates to 30 degrees, then we'll be able to define the coordinate for this angle rotations pi over 6 radian using the right triangle ratios we already talked about in our previous videos. Then it will be square root of 3 over 2. So if you write a little bit upside, the square root of 3 over 2, 1 over 2. So after moving this up, let's think about what are the values. So obviously the square root of 3 over 2 in the x positions will be the following cosine of the main angle pi over 6 radian, just like we learned. And 1 over 2 will be the value for the sine of the main angle, pi over 6 radian, which is 30 degrees in terms of degree mode. So we could solve the square root of 3 over 2 is the cosine of pi over 6 radian, 1 over 2 as sine of pi over 6 radian. Now let's think about this second special angle, pi over 4 radians, rotated from the starting line, which is 45 degrees. So this blue line, let's assume that that angular rotation is pi over 4 radian. And again, the pi over 4 radian is 45 degrees, just like we know. When it is pi over 4 radians, then it is 45 degrees, and according to the property we already talked about in the previous videos, then the following coordinate for this term when the main angle is 45 degrees is going to be square root of 2 over 2. So this one will be square root of 2 over, not over, but comma, square root of 2. And if you think about its values, the square root of 2 over 2 in the x position is going to be the cosine of the main angle, pi over 4 radians. And the square root of 2 over 2 inside the y position is going to be the sine of the main angle, pi over 4 radian. So we can figure out that according to what we learned, square root of 2 over 2 and the square root of 2 over 2 is a cosine and a sine of the main angle, pi over 4 radian respectively. And this is what we learned in the previous videos. Now let's think about the lost angle rotations in the special angle, which is 60 degrees, or another way to say pi over 3 radian. So after arranging these positions for spaces, let's think about the angle rotations pi over 3 radians. So as you can see, I rearranged this unit circle by putting it a little bit down for spaces. And let's say this red line, it has the angle rotations of pi over 3 radians. And obviously pi over 3 radian is 60 degrees in terms of degrees. And according to what we learned in our previous videos, we can define what is this coordinate, x, y. Well, when the angle rotated pi over 3 radian, then the coordinate will be 1 over 2, square root of 3 over 2. And again, the 1 over 2 is the value for the cosine. The 1 over 2 inside the x position is the cosine of the main angle, pi over 6 radian. And the square root of 3 over 2 inside the y position will be the sine of the main angle, pi over 6 radian. And by solving this, we could be able to review the pi over 4 radian, pi over 6 radian, as well as pi over 3 radians, which are the special angles. And we could define the x and the y coordinate using the property of the unit circle. Now, using this information and the knowledge that we used to graph the previous video's graph, which are sine x and the cosine x, let's start graphing the y's tangent x. So before we do it, we already know that in our previous videos we defined using the properties of the unit circle, where the radius is 1, which I'm not going to explain right now. And if you're not familiar with it, you need to go back to my previous videos about graphing the sine or cosine function, or you can also go to the what is the unit circle. And because the x, y are a cosine and a sine, we define that the cosine theta is the x coordinate or the x value only inside the unit circle. The sine of the main angle theta is the y coordinate. And lastly, the tangent of the main angle theta is same thing with the y over x, where y is sine over cosine. And again, y over x, we saw in a lot of chapters already inside the functions, where if you're thinking of the y over x, it is same thing with thinking of a slope, how steep the function is, mostly inside the linear functions. So that means inside the trigonometric functions or on the unit circle, we defined the tangent data as a slope of a trigonometric functions. And the reason why I'm explaining the tangent in more detail than cosine and sine is because the y's tangent data is what we're going to graph in this video. So now let's think about one coordinate plane with the x and the y axis, which I'm going to explain right now. So here is the x and the y axis, and what we're trying to graph is y is equal to tangent x graph. So we've just so far graphed the two trigonometric functions, sine and a cosine value, so we will know what the x and the y value inside this tangent x is. Well, what is the x that starts from negative infinity and reaches to the positive infinity? Well, we already know that the x value inside the tangent x and whatever the trig value, sine, cosine, and tangent, It is the angular rotations that can rotate from the starting line either positive infinity directions or the negative infinity directions. So this angular rotation is going to be the x value. And again, a lot of people get confused with this idea where this x value inside the y's tangent x or a y's sine or a cosine x, it is the angular rotations on the unit circle. But people might be confused with the x value inside the unit circle and the x value inside the y's tangent x. But it's completely different. The x value inside this unit circle is the value of cosine theta, and the x value inside the tangent x is going to be the angular rotations, just like I mentioned right now on the unit circle. So that is the one point that we need to be care of. But as we can see, the angle can rotate either positive or negative infinity direction. That means the x that starts from the negative all the way to the positive infinity, that will be all real numbers. That means there is no limitation inside the domain. But what about the y value? The y value that starts from the y all the way down. But unfortunately, just like y sine x and cosine x, also the y's tangent x has a little bit limitations inside the y is equal to tangent x y value. And we'll be able to know what that is and what the limitation is after I graph one period of y's tangent x. So after rearranging these values, let's start graphing one period of y's tangent x. So I've just graphed a one period of y's tangent x. So firstly, the basic graph of y's tangent x is it starts from the negative pi over 2 radian and finish at the pi over 2 radian. So that means we can realize that the one period for y's tangent x is pi radian. That is different with y's sine x or cosine x, where their period is 2 pi radian. And also it starts from the 0. And the graph or the curve that keep going up on and on and on, that means inside the y's tangent x, which is a collection of the slope. In the trigonometric functions, the slope gets bigger, but as we can see the dashed lines where it has the pi over 2 radian in it, that means the pi over 2 radian is an asymptote. And also, in the opposite side, where from the 0 as the line or the line gets bigger, but it will never intersect with the dashed line, which is a negative pi over 2 radian. And the dashed line where the graph never intersect with, that is where we call it as an asymptote. And the asymptote will be made when the value is undefined, and the undefined value means the denominator is equal to 0. So to think about why all these things happen, now let's compare y's tangent x graph with the unit circle to think about y's period of pi radian and why does it have any asymptotes. Firstly, let's think about why is there any asymptote in it, as pi over 2 radian and negative pi over 2 radian in the first period of y's tangent x. And the reason is because as the angle starts from 0 and keep increasing, and as it finally reaches the pi over 2 radian, which is 90 degrees, so let's say as the angle increases, such as from pi over 6 radian to pi over 4 radian, all the way to pi over 3 radian, and as it finally gets to pi over 2 radian, which is 90 degrees right over here, what will be the tangent value? We already know that the coordinate is 0, positive 1, where the cosine of the pi over 2 radian is equal to 0, and the sine of the pi over 2 radian is equal to positive 1. But we already know that inside, when we're thinking of the tangent of the main angle, pi over 2 radian, that is same thing with saying, just like I mentioned here, sine of the main angle over the cosine of the main angle. So sine of the main angle, pi over 2 radian, over the cosine of the main angle, the cosine of the main angle pi over 2 radian. However, we can figure out that what is the sine pi over 2 pi over 2 on the unit circle. That is equal to 1 because sine is equal to y coordinate. And over what is the cosine of the main angle pi over 2 radian? Well, that is equal to 0 because the cosine of any angle measurement is 0 on the unit circle. So it will be 0. But there is no such value where we can divide 1 by any number by 0. That is the undefined value. It does not exist either in the graph or in the coordinate plane. That's why when it gets to the pi over 2 radian, as the angle increases from the 0, then the point where the graph approaches pi over 2 radian, but it will never intersect with it. That's why the pi over 2 radian is an asymptote. However, before it gets to the pi over 2 radian, the slope inside the unit circle will keep increased until it gets to the pi over 2 units. So that's why from the 0, the graph increases all the way to pi over 2 units. Now let's think about the graph that decreases from 0. As the angle decreases from 0 and reaches negative pi over 2, as we can see from the graph that is shown below, it has an asymptote. And the reason is because, just like we showed here, from the negative angle means from the 0, we're going to the negative or clockwise directions. So let's say we're going to clockwise directions, then the slope of the tangent graph, just like we learned in the previous videos, that will be decreasing. So as it decreases, it will keep decreasing until it gets to the pi over 2 radian. What will happen if it gets to the pi over 2 radian? Well, we can figure out that when we're trying to solve for the tangent of any main angle, so let's say the tangent of the angle 3 pi or negative pi over 2 units. That is same thing with saying the sine of the main angle negative pi over 2 units or a radian over the cosine of the pi over negative pi over 2 radian. What is the sine of negative pi over 2 radian? Well, we already know that the sine of the main any angle measurement is the y coordinate. In this case, when it is negative pi over 2 radian, which means from the starting line, you go negative direction or a clockwise direction pi over 2 units. So sine of negative pi over 2 units or a radian is negative 1 over the cosine of negative pi over 2 is the x value. The x value is going to be the cosine of the main angle, which is negative pi over 2 radian in this case. However, we cannot divide any numbers by 0. That will be the value that does not exist, which is an asymptote, or we can say undefined. So that's why as the angle decreases to the clockwise directions, the graph, which is a slope as a tangent inside the unit circle, will keep decreasing until it approaches the negative pi over 2 radian. That is an asymptote. That means even though this graph approaches the negative pi over 2 units, that will never intersect with it. So from the negative pi over 2 radian, pi over 2 radian, that will be the value or the graph of y is equal to tangent x graph with a period of pi radian. So using this information, let's think about the properties that we know so far about the y's tangent x graph. So whenever we're thinking of the y's tangent x graph or whatever the graph of trigonometric functions, we always like to think about the main 3 things. The domain that shows the what are the all set of values we can input the x value to satisfy the graph. Second thing is the range. If the domain is all set of x value we can input, then the range will be the all set of output we can get from the graph. And lastly, the most important thing inside the trigonometric function, which is a period. And the period means after a certain form is formed inside the graph, which is in this case y is tangent x, they'll be continuing to the positive and negative infinity directions. So for the domain, just like y sine or cosine x, what is the domain for the y is tangent x? Well, we already talked about it before we started the graphing. From the negative all the way to the positive infinity directions, the x value will be the angle rotations, the angle that can rotate either negative or the positive directions. So that means it does not have any limitations. We can write it as all real numbers. So even though it's all real numbers, but when you look at the range, just like y sine x and y cosine x, it has a limitations. The reason is because even though from the positive and negative infinity, if you just think about just graph, there is no limitations. However, now we can figure out that because the tangent x is a slope, for example, in the first period, when it is pi over 2 units, and a negative pi over 2 radian, there is an asymptote. That means the range will be the all real numbers. The range will be the all real numbers, except, which means not including the asymptote. And again, the asymptote, just like we learned in the rational functions, the asymptote means the function value in that interval is undefined. And the reason why it is the tangent undefined is because just like pi over 2 radian or negative pi over 2 radian, those tangent values suggest tangent of pi over 2 radian, and the tangent of negative pi over 2 radian has the undefined value, since we know that the value in the denominator is equal to 0. So that was the range. What is the period? Well, just like we can see, from the negative pi over 2 radian all the way to the pi over 2 radian, the period for the y's tangent x is going to be pi radian. That is different with the sine or cosine x, because sine or cosine x has the period of 2 pi radian. So I will explain why the period is pi radian in the next video, where I'm going to explain a little bit more about the properties of y's sine x, y's cosine x, and y's tangent x to compare them together. But now, you need to just know 3 things here: the domain, range, and the period, where the period is pi radian. That means from negative pi over 2 radian to the pi over 2 radian, the period of pi, this format where occurring to the 0, which is the origin, the left side to the pi over 2 radian, negative pi over 2 radian, has a slope that is decreasing, and when it's negative pi over 2 radian, that will be an asymptote. And for the right side, as the slope of a y's tangent x increase, but will never intersect at pi over 2 radian, this graph with the period of pi will be continued to the positive infinity directions and also the negative infinity directions. However, for matter of spaces, just like I did in the previous videos, right now, after arranging these drawings, because it's kind of messed up right now, I'm going to graph one more period of y's tangent x to get a kind of an idea how that graph of y's tangent x repeats. So this is a graph that has a 2 period of y's tangent x graph. So we already know that the first period we already graphed was from negative pi over 2 radian all the way to the pi over 2 radian with the period of pi radian, where the pi over 2 radian and the negative pi over 2 radian with the dashed line in it is going to be an asymptote where the graph keep approach but never intersect. And there is another period of graph from the pi radian, which is just like the origin in this graph where I'm pointing right now. According to the pi radian, the graph has the same form, where it has the period from pi over 2 radian all the way to 3 pi over 2 radian which has a period of pi radian, then the case where the 3 pi radian will be the asymptote, and the pi radian will also be an asymptote. And according to the main point where the x value is pi radian, the left side of the graph will keep decreasing, and it will keep approach the pi over 2 radian, but it will never intersect with it because that is a asymptote inside the y as tangent x graph. The second thing is, if you look at the right side of the graph, as it keeps increasing, then as it gets to 3 pi radian, when it's 3 pi radian, it will have its asymptote as 3 pi radian. That means this graph will keep approach through it, but will never intersect with the 3 pi radian. So we've graphed 2 periods of y's tangent x from negative pi radian all the way to pi radian, and from the pi radian all the way to 3 pi radian. So last thing we're going to talk about before we review and finish this lecture, it is going to be what are the asymptote. And if you see the pattern, what is the asymptote? How can we notate it in terms of just one simple expression? We simply notate the asymptote as n times pi plus pi over 2 radian. And the reason is because the n value is a constant that can be either negative or positive times pi plus pi over 2 radian. So let's apply it simply to the asymptote of y's tangent x. Firstly, when we're thinking of the negative pi over 2 radian, that will be the case when the n value is equal to 0. When the n value is equal to 0, then they will be pi over 2 radian. Not pi over 2 radian. So the best way to explain or notate the asymptote is to say n pi plus pi over 2 radian. And where the n is a constant that can be negative or a positive value. So for example, like this. Let's apply this to the y's tangent x graph firstly. Let's say when the n value is negative 1. Then the following value will be negative pi, where the n is equal to negative 1, plus pi over 2 radian. That gives us negative pi over 2 radian, which thus equal to negative pi over 2 radian as an asymptote inside the y is equal to tangent x. Now let's think about when the n value is equal to 0. Then n times pi is 0 plus pi over 2 will be pi over 2 radian, where pi over 2 radian thus equal to an asymptote. Lastly, let's say the n value, which is a constant, is equal to for example 1. Then 1 times pi is pi plus pi over 2 radian. That is going to be 3 pi over 2 radian, which is right over here, and that does equal to an asymptote of y's tangent x. So these 4 things, domain, range, period, as well as the asymptote, that are the only tangent x properties we need to remember. So let's review what we have done so far. So firstly, we were trying to graph the y's tangent x, which is a lost trigonometric function graph. So on the unit circle, we already defined that cosine theta and the sine theta are the x and the y respectively. So cosine theta is the x value, sine theta is the y value. What is tangent? That is y over x, another way to say sine over cosine. And we saw y over x in a lot of videos, where y over x is the slope for the linear function. In this case, the slope for a trigonometric function on the unit circle. And as the so we graphed the y's tangent x. Firstly, the first period of y's tangent x starts from negative pi over 2 to the pi over 2 radian. That makes the period as pi radian. The domain, which shows all the possible x value we can input, it is the real number. And that is because from the negative to the positive infinity direction, those are the angle that can rotate on the angle or in a circle. And we always need to be careful that the x value is sidewise tangent x, and this x value on the unit circle is completely different. The x value on the unit circle is the cosine theta, and the x value is sidewise tangent x, also other trigonometric function. This x is going to be the angular rotations that can rotate positive or negative infinity directions. And when we look at the range, which is all set of y value we can input, it was all real numbers except for the asymptote. And the reason why it has the asymptote is because it has a special interval where it is undefined. So for example, negative pi over 2 radian and pi over 2 radian. So we could express the asymptote as a simple equation n pi plus pi over 2 radian, where the n can be a integer from negative to the positive value. So this was the basic introduction to the y's tangent x graph, and in the next video where I'm going to explain a little bit more about y's tangent x graph, y's sine x, and y's cosine x, to compare them and think about the transformation and translation basically to solve for the question.